I am going to discuss about recurrence relation in this video. A recurrence relation is nothing but it is a mathematical expression that defines a sequence in terms of its previous terms. In the context of algorithmic analysis, this recurrence relation is often used to model the time complexity of recursive algorithm, not an iterative algorithm. So, where exactly we will be framing the recurrence relation means where the recursive procedure is followed in the pseudocode. Generally, to solve any problem, either we can go with iterative procedure to solve the problem, otherwise we can go with the recursive procedure while framing the pseudocode. If you take binary search, the binary search problem can be solved using both iterative method as well as recursive method. If you take the pseudocode algorithm where the iterative procedure is involved, it is very easy to trace the pseudocode. Line by line we can trace the pseudocode and we can compute the time complexity very easily, and also we can go with the operation count also to identify the time complexity where the iterative procedure is involved. When it comes to the recursive procedure, means that where the recursive function calls are used in the pseudocode, it is not possible to trace the pseudocode line by line to analyze to find the time complexity. So, in such scenario, we are supposed to frame the recurrence relation for the given pseudocode. So, especially when we use the recursive function inside the pseudocode, we cannot trace the pseudocode directly to obtain the time complexity. We are supposed to frame the recurrence relation. So, how to frame the recurrence relation would be discussed later. Now, let me tell you what exactly the recurrence relation is and what is the significance of recurrence relation in data structures and algorithms, and also why it is so important. So, where the recursive function is involved, we have to frame the recurrence relation, and then only we can derive through which we can derive the time complexity. So, how the recurrence relation can be derived? With the help of some methods only, like substitution method, recursion tree method, Master's theorem method, there are different methods are there to solve the recurrence relation through which we can derive the time complexity. Before that, let us see what are the significance of recurrence relations in data structures and algorithms. Recurrence relations play a significant role in analyzing as well as optimizing the complexity of algorithms. Having a strong understanding of recurrence relations play a great role in developing the problem solving skills of an individual. Some of the common uses of recurrence relations are, it helps to analyze recursive algorithms, that is number one, and the second significance is time complexity analysis. It helps to analyze the time complexity of an algorithm, and the third point is to generalize the divide and conquer algorithm, the recurrence relations would be used. It is one of the final the significance of recurrence relations in DSA. Why recurrence relations are framed? The very first step is the reason is analyzing the time complexity. Recurrence relations are particularly useful for analyzing the time complexity of algorithms only, especially for the recursive ones, especially where the recursive procedure is involved in the pseudocode. They allow us to express the time required to solve a problem of size n in terms of the time required to solve smaller instances of the same problem. This analysis is very crucial for understanding how an algorithm performs as the size of the input grows. The second reason is for comparing algorithms. By analyzing recurrent relations, we can compare different algorithms for the same problem. So, for the same problem, different algorithms, different techniques can be used, right. So, by analyzing the recurrence relations, we can compare different algorithms for the same problem and determine which one is the efficient one, which one is more efficient. This is essential for making informed decisions about algorithm selection, especially when dealing with large data sets or time critical applications. The third reason is optimization opportunities. So, recurrence relations often reveal patterns and dependencies within an algorithm, which can lead to optimization opportunities. Understanding these relations can help identify redundant computations or inefficiencies which can be eliminated to improve algorithm performance. So, these are the reasons why the recurrence relations are framed. And also, as I discussed before, to solve the recurrence relations, there are several methods are there, each suitable for different types of relations and complexities. So, here are the some common methods used to solve the recurrence relations. One is substitution method. This method involves guessing a solution and then proving it correct using mathematical induction. It is particularly useful for simple recurrence relations or when a pattern can be easily identified. So, for instance, this substitution method would work effectively on the recurrence relations where the decreasing function is involved. I will discuss later, like let me tell you like what exactly the decreasing function is and the dividing function is. So, this would work effectively on the recurrence relation where the decreasing function is involved, and the second method is recurrence tree method. This method works effectively on the recurrence relations where the dividing function is involved. And Master's theorem is one of the easiest method. It provides a general framework for solving the recurrence relations. So, this is applicable on any recurrence relation which involves any function. So, it can be applied on both the decreasing as well as dividing functions. Now, let us discuss what exactly this decreasing function is and what exactly the dividing function is. For example, let us take a Fibonacci series. To print Fibonacci sequence, we can write the pseudocode using the recursive function calls as well. Let us write the pseudocode for finding out the Fibonacci series. So, to print the Fibonacci sequence, let us write the pseudocode. Let me tell you what exactly the decreasing function is, how the recurrence relation with a decreasing function would look like. This is the pseudocode. Fibonacci sequence for n, I just want to identify. If n is lesser than or equals to 1, it would return n only. If n is greater than 1, it will go to the else part, it would return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So, this is the recursive call, right. So, if you look at the pseudocode, the condition here is for n you want to identify. For example, I want to print Fibonacci of 5. The output is going to be this is going to be the output. So, for 5 I want to identify. The condition given here is, this is the base condition. If n is less than or equals to 1, it would return n. Otherwise, else it would go to the else part, return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So, this would be recursively called every time, right, until we reach the base case. This would be recursively functioned, right. So, how the recurrence relation can be framed for this Fibonacci sequence? This is going to be the recurrence relation. F of n equals to, every time, like we are calling Fibonacci of n minus 1 and n minus 2, this we call it as the decreasing function. Here n minus 1 and n minus 2, this is the decreasing function here. So, every time we are reducing it, right. So, we call this as a decreasing function. When we write the recurrence relation, how the recurrence relation can be framed. This is what going to be the recurrence relation for to print the Fibonacci sequence. because if you trace the pseudocode, you very well know that this is going to take some constant amount of time. For every function call, it is going to get executed for one time, right? And if you check the else part here, there is a recursive function involved. You have no idea how many number of times this recursive function would be called, because every time this would be called here. You will call these two n minus 1 plus n minus 1 plus n minus 2, these two would be summed up, and the sum value would be passed here in the place of n again, right? So when there is a recursive function involved, it is not easy to trace the pseudocode, it is not easy to identify how many number of iterations the so and so statement is going to take. So the only way, the preferable way is to identify the time complexity is by framing the recurrence relation only. How this can be written? F of n minus 1 plus f of n minus 2 plus these two are recursive procedure plus this one. This is the recurrence relation to frame the Fibonacci sequence. So now it is recursively getting called when it would end, when it reaches the base case. So what is exactly the base case is, because we need to establish base case to define the initial values of the sequence. Typically the Fibonacci sequence starts with 0 and 1. So the base cases are, the condition given here is n is lesser than or equals to 1. So when n is lesser than or equals to 1, the function ends here, right? When it is not lesser than or equals to 1, we go to the next step, to the else part, to perform the recursive call, right? So when exactly it would end? When we reach the base case, and this is the base case here. So along with the recurrence relation, by default we are supposed to represent the base case as well, so that we would know like where exactly the algorithm would end, when exactly the algorithm would end. The base case here is when your n value is 0 or when your n value is 1, the value is going to be 1. Otherwise we are supposed to use this recurrence relation to derive the time complexity. This is how we are supposed to frame the recurrence relation, and this is the recurrence relation where the decreasing function is involved, because here we are decreasing one value here and here decreasing two values. So this is how the recurrence relation with the decreasing function would look like. To solve this, this also can be written as t of time taken to solve the input size of n. So f of n represents the Fibonacci number. This n minus 1 represents n minus 1th Fibonacci number. This represents n minus 1th Fibonacci number, and this represents n minus 2th Fibonacci numbers, and this f of n represents nth Fibonacci number. So this can be written as f of n equal to f of n minus 1 plus f of n minus 2, otherwise t of n equal to t of n minus 1 plus t of n minus 2 plus 1 and the base case is t of 0 equals to t of 1 equals to 1. So this is the recurrence relation. You can write it in either way for framing Fibonacci sequence. So this is the example recurrence relation where the decreasing function is involved. We can go with the substitution method to solve this. Okay. Now the next type is going to be the recurrence relation where the dividing function is involved. Let's take binary search. If you take binary search, for example 5, 10, 15, 20. Let's take binary search. This is the example. So usually in binary search what we do means we'll write the key element. For example, the key element 15 I want to identify. The very first step is, in the binary search we are supposed to identify the mid element, as we all know. I already would have discussed in the previous lecture. So identify the mid element. Here the mid element is 0. So if you identify the mid element low plus high by 2, the mid element is going to be 1, which means this is going to be the mid element. Every time it would compare the key value along with the mid element, whether the mid and the key value is equal. No, if it is not equal, the list would get divided into 2. The element right from the low till mid minus 1 is one subproblem, mid plus 1 till high is going to be another subproblem, and also this binary search is applicable only on the sorted list, right? If the mid element is 10, right? Mid element, you have to compare the mid element along with the key element. If you, when you compare, if the key value is greater than the mid element, we are supposed to concentrate on the right hand side, because it is already in the ascending order, sorted order. If it is greater, definitely right hand side of the mid only the key element is going to be. So we ignore the left sub problem completely, since the key element is greater than the mid element. We ignore this completely and we concentrate on only the right sub problem, and then again we identify the mid element. After identifying the mid element, again we would be comparing. For instance, again this is the mid element, means if it is equal, yes, the key value would be printed. Suppose if it is 20 or some other element, again you have to compare it. If it is greater, left hand side again would be completely ignored. If it is lesser, again the right hand side would be ignored. So every time we are getting the problem size of n by 2. If the problem size is n, every time we are dividing it to n by 2. So every time we are getting two problems with the size of n by 2, right? 2 problems you are getting, but we are concentrating on only one, because one problem we are completely ignoring and we are solving only one problem. So time taken to solve only one problem only you have to consider here. When you compute the time complexity, you are supposed to compute the time taken to solve only one sub problem in each iteration. Now how the recurrence relation can be written for the binary search? Every time we are dividing the functions, we are dividing the problem. Since you are dividing the problem every time, when you write the recurrence relation, the dividing function only will be involved. For example, if the problem size is n, every time after finding out the mid element and making the comparison, if mid element and key is not equal, the list is immediately getting subdivided into 2. We are getting 2 different sub problems, right? What is the size of the sub problem? It is n by 2. So the size is n by 2. In each iteration, how many number of problems you are solving? You are getting 2 sub problems, 2 n by 2 sub problems we are getting, but how many problems we are solving? We are concentrating on only one. So 1 t n by 2 plus big O of 1. This indicates, already we would have discussed again in the previous lecture, the constant time for performing the comparisons and updating the indices. So this is how you are supposed to write the recurrence relation for binary search, and this is the example recurrence relation where the dividing function is involved. And this TFN, you all know, it represents the time complexity, time taken to solve the problem with the size n, with the input size n. This n by 2 represents the problem, sub problem size. This indicates the number of sub problem we are going to concentrate on each iteration. And this one is for performing comparisons. This is the example recurrence relation where the dividing function is involved. And to solve this, recurrence tree method is going to be the efficient one. The same function, the recurrence relation, can be solved using substitution method as well, but recurrence tree method works better on this. First method is substitution method to solve the recurrence relation, second method is recurrence tree method, and third method which I have mentioned here is Master's theorem. This is going to be the easiest one, the easiest method to solve the recurrence relation. Using this Master's theorem, we can solve both the recurrence relation, like both the relations where both the decreasing function as well as the dividing function is involved. In the upcoming video, let's discuss few example problems under the substitution method, and also let's discuss the Master's theorem also in the upcoming lecture. Thank you.